Okay. Okay. Okay, so before we proceed with the lecture, I just want to give an important instruction regarding evaluation. So this week, you might probably in the lab session, you might have an evaluation. So be ready with your preparation for the lab. Okay, anytime you might be instructed for the evaluation, so just be ready. And other than that, regarding the GitHub repository links that you have shared with me on the evaluation section, it is instructed that you make your repositories private. Okay, so everyone, whoever has shared your repository links with me, are requested to make your repositories private and add me as a collaborator in your repository. Okay, so I have already made that instruction, made you aware of that instruction in the evaluation one, where I have added this instruction. So just follow that instruction. And one more thing, so some of you, around 37 people, haven't submitted your repository links as of yet. So make sure that you do it as soon as possible, because it will be taken into consideration for your evaluation. Okay, internal evaluation that will be taken. So I suppose everyone is clear with the instruction that I just gave. Yes, yes or no? Just acknowledge whether is everyone clear with the instruction. Okay, fine. Okay, so yes, so what I just said is, so for those of you who have shared with me your repository links, just make your repositories private and add me as a collaborator in your repository so that I can see your work, whatever you have done. You just have to make your repositories private and add me as a collaborator. Some of you have already added me as a collaborator but haven't made your repositories private yet. So what you are instructed is, you are instructed to make your repositories private and add me as a collaborator. In the instruction section of evaluation 1, I have already written my user ID, which is Varlakshmi Iyer CE. So you have to, yes, in the instruction section of the evaluation 1, I have shared my user ID. Okay, so you have to add that user ID as a collaborator in your repository. Okay, so make sure that you do that and you make your repositories private so that I can check your work that you have done. And this week you might probably have your evaluation, so just be ready with your preparation for the evaluation of your ML. And another thing that I wanted to tell is, yes, might be during lab, or maybe I'll give any further instruction if required during the week through the classroom. So keep checking the classroom as well. Okay, so most probably during the lab, or maybe it could be other time as well. Okay, just keep checking the classroom for further instructions. And also 37 people out of all the students haven't submitted their repository links as of yet, have been submitted. So make sure that you do that, and it will be taken into consideration that whoever hasn't submitted yet. So make sure that everyone submits the repository link and also follows the instruction that is given to you. That is, you have to make your repositories private and add me as a collaborator. Okay, I suppose everyone is clear now with the instruction. All right. Fine. So let us start with today's discussion with a brief introduction to what we discussed in the previous lecture. So in the previous lecture, we got a brief introduction of multi-layer perceptron, which is, and we saw that why we got introduced to multi-layer perceptron, right? So we saw that there was some XOR problem that we were facing by utilizing a single layer perceptron was not able to solve an XOR problem. So we got introduced to a multi-layer perceptron. So if you remember, the multi-layer perceptron was containing of multiple layers, which is first is input layer, then you have hidden layer, followed by input layer, you have hidden layer, and after hidden layer, you have output layer. You may have more than one hidden layer in your multi-layer perceptron as well. And we started our discussion that how to so we started our discussion with forward. There are two passes that is present in your multi-layer perceptron in order to perform in order to reduce the loss. So first process that will be performed, let me share the screen first. So I suppose the screen is visible to all. Yes. Okay. Okay. So our discussion was. So we started our discussion about multi-layer perceptron, in which we saw that there are two passes, which is forward pass and backward pass. Okay. So if you share this analogy with linear regression, just I want to share this analogy with linear regression model. Then if you recall, then in linear regression, what we did is we first calculated what is the output that the model is predicting based on the input that is provided to the model. And based on the output, what you do is calculate the loss that the model is that you get after finding an output through the model, and you're comparing your output, your predicted output, with the actual output of your data set. Then you calculate the loss, and based on the loss, what you are trying to do, you are trying to find the values of the parameters such that your loss is minimum. Okay, find the value of parameters such that your loss is minimum. So you are trying to update the values of parameters to minimize your loss. And one of the methods that we saw to minimize to find the values of optimal values of parameter was gradient descent algorithm that we utilized to find this values of the parameter. So if you share the same multi-layer perceptron is sharing the same process. So we have two steps here. We have forward pass, which is actually similar to calculating the loss that the model is creating. Okay. So what we'll be doing in the forward passes, we'll be passing the inputs through the multi-layer perceptron model that we have created. That is, we will calculate what is the output that is generated through the model, and then we'll calculate what is the loss that is obtained by passing the by for this particular input. Okay, based on the target output, actual target output that we have present in our data set. Okay, we'll calculate what is the loss, and what is the backward pass doing. Backward pass is actually passing your error back into the model so as to update your weights. Okay, so what is the main idea behind backward passes? We'll try to use the gradient descent algorithm. That is, we'll try to use this gradient descent backward. That is, you'll pass the error back into the model in order to calculate what is the what is the updated, what is the weight, what is the new value of parameters that I can obtain in order to minimize the loss. Okay, in order to minimize the loss. Along with this, we saw some of the activation functions as well, if you recall, which activation functions can be used in the output layer. What are the activation functions that you can utilize in the hidden layer, and what activation function you may not you cannot utilize in the hidden layer. Okay, if you recall, linear activation function we discussed we cannot utilize in the hidden layer because main purpose of this hidden layer is to is to inherit the non-linearity in the present in the data set. Okay, up to this everyone is clear, right? The backward pass and forward pass, everyone is clear up to this? Yes or no? Okay. So now our discussion after this was a derivation. Okay, we were trying to perform the derivation process, in which we first performed the derivation. If you recall, we defined our loss function. If you recall, this was our loss function for the model. We also defined the activation functions for our hidden layer as well as the output layer. First, I'll be starting with a simple example of a multi-layer perceptron that I have defined. Okay, I started my discussion with this multi-layer perceptron, this particular model that I have created, in which there are two inputs, there is one hidden layer and there is one output layer. There are two neurons in the hidden layer and one neuron in the output layer, right? So first, we started our discussion with the derivation for this particular model. The main idea behind gradient descent is to, what is the change? Suppose if I change a particular weight, what is the change that I'll be seeing in the loss? What is the change that I'll be seeing in the loss by changing a particular weight? So in the first discussion that we saw, we tried to make changes in this particular weight. Okay, this particular weight. So we actually calculated, if you recall, del Li upon del W12. That was our discussion. Last time we performed the derivation for this particular value. That is what is for this particular value. So if you create an analogy with the case of linear regression as well, we are, if you recall, in the case of linear regression, what we were trying to do, we were trying to update the values of parameters. What is the parameters that we had? Theta 0, theta 1, these were the parameters that were present in the case of linear regression. And if you recall, we were calculating the gradients with respect to all the parameters so as to update the values of the parameter. And we had a certain formula to update the values of parameter, which was theta 0 is equals to theta 0. This new values of parameter theta 0 is equals to minus into alpha del L, sorry, del J upon del theta J. Just consider J here. Okay. So this was our update rule, weight update rule for the case of linear regression. And similarly, we'll be having a similar weight update rule in the case of multilayer perceptron as well. But for that, we need to calculate these gradients values. Okay, we need to calculate this gradient value. So we calculated the gradient value with respect to the first weight, that is the weight that is in the connection from hidden layer to the output layer, that is W12. Okay, we calculated the what is the gradient chain rule formula. So if you recall, we performed the discussion that making a change in the value of W12. Let us go through the so this was the chain rule formula that we had. So if we make a change in the case of W12, if we make a certain change in the case of W12, then it will impact the value of Z2, which Z2, if you recall, Z2 was defined, what was the definition of Z2 that we had is, this was the definition of Z2, which is W12H1 plus W22H2. Okay, if you recall the multilayer perceptron that we had defined. So this was the value of Z2. And if we make certain changes in the value of Z2, then it will impact the value of Pi hat, which is the output, which is actually the sigmoid of Z2. Okay, sigmoid of Z2. I'm just revising the concept that we had discussed in the previous lecture. So if you face any difficulty in the following, what we are going to follow today, that will be solved. Okay. And making a change in Pi hat will ultimately make changes in the value of loss. Okay, so this was our chain rule that we had defined in the case of W12. Is it clear? This was clear. This was clear. Then we perform the derivation for each of these cases. For example, with the case of delta Z2 upon delta W12, if you recall, what was the derivation? So this was this is a chain rule that we have defined. That is, W12 will impact the value of Z2. Z2 will impact the value of Pi hat, which is the output that is predicted through the model, predicted by the model, output predicted by the model. And ultimately, this value will impact the loss that is being calculated by the model, right? Okay. So if you recall, we calculated the derivation for each of these cases. Since Z2 is equals to W12 H1 plus W22 H2, so derivation with respect to W12 will be equals to H1. Okay. Similarly, Pi hat with respect to Z2. And if you recall, what is Pi hat? Pi hat is sigmoid of Z2. So if you recall, what was the derivation of sigmoid? What was the derivation of sigmoid? Sigmoid is this formula. Okay, sigmoid. For example, just a case, if sigmoid is equals to 1 upon 1 plus e raised to minus x, the derivation of sigmoid with respect to x is equal. Yes. Is anybody? Yes. All right. Derivation of sigmoid with respect to x is equal to sigmoid into 1 minus sigmoid. Okay, this is a derivation with respect to x. So here we have Pi hat. So the Pi hat with respect to Z2 will be Pi hat into 1 minus Pi hat. Okay, and we also already know what is the derivation of loss with respect to Pi hat, which is Pi hat minus Yi. So we kept these all values in the derivation, and this is the final value that we are getting. This is the final value that we are getting for del Li upon del W12. Okay, this is the value that we are getting. Okay, up to this, anyone is having any doubt in the derivation or in the chain rule that we implemented? Anybody is having any problem in the derivation or the chain rule? Okay. I suppose everyone is clear with this. So now we are proceeding with the hidden layer process. This was for the output layer. If anyone is having any doubt, just let me know right now. Okay. Shall we proceed with the next part, with the hidden layer part? Now, so I have kept this clear in the PPT. When I'll be sharing the PPT, you'll get more idea. Maybe some of you are finding it clumsy at this point of time. But I suppose the idea is clear to you, right? The chain rule idea is clear to you up to this, that how we are proceeding with the chain rule. Yes or no? Okay. So as we saw that this is the first part that we are doing. That is, we are finding the weight update with respect to the output layer. Okay, with respect to the output layer that we have. Now, what to do in the case of the hidden layer? So in hidden layer, if you see, in the case of hidden layer, if you see, we do not have any error, any output associated with the hidden layer. In the case of output layer, we have an output associated with it. We have a target value associated with it, because of which we can calculate the loss. But in the case of hidden layer, we do not have any target value. Okay, we do not have any target value associated with it. So that we cannot calculate loss in the case of hidden layer. So what is the point? What is how do we calculate? How do we update the weights associated with the hidden layer? The main idea would be to propagate the error backwards. That is the main idea. That is the idea behind back propagation. That is, we are going to propagate the error backwards so that we can calculate the weight update rule associated with the hidden layer. Okay, we are going to propagate the error backwards. Now we'll see through the chain rule that this is being done in the case of hidden layer as well. So if you see, suppose let us go to the chain rule for the hidden layer. Now, let us consider this particular multi-layer perceptron that we have at this point of time. This is the multi-layer perceptron that we have defined at this point of time. So what we are doing is we are calculating with the help with the output layer. We have a loss associated. We have a loss associated with the help of with the output layer, and we are propagating this loss backwards, and we are calculating the weight update rule with the help of with the last layer. Since we have a loss associated with this, it is quite easier to calculate the weight update rule for the case of the connection between hidden layer and the output layer. But we do not have any loss associated with the input layer and the hidden layer. So how to do it? So what we'll be doing is we'll be propagating this loss backwards. Okay. So if we calculate the entire chain rule, for example, suppose I want to update the weight W111. Okay. Suppose I want to update this weight. Okay, suppose I want to update this particular weight. Then how do I proceed? So if you recall, what was the chain rule formula? What is the chain rule formula that we had in the case of a similar chain rule formula will be derived in the case of this also. So if you see del Li upon del W12, okay, sorry, W11, this is wrong, W111. Okay, del Li upon del W111. Okay, this is the weight update. This is the gradient value that we are calculating. The gradient value that we'll be calculating for updating this particular weight. Okay, this particular weight to update this particular weight. So if you can see, what will be the chain rule that we'll be seeing in this case is, for example, let us see. So if you see, if you make certain changes in the value of this weight, then it will directly impact the value of Z11 that we are calculating. And I have already written the formula of Z11 and Z12. What is Z11? Z11 will be the output of this hidden layer. Okay, the value that is being calculated, the weighted sum that is calculated for this particular hidden layer, and Z12 will be the weighted sum which I will be calculating for this particular hidden layer, which is W11 for this particular hidden layer, which is W111 into X1 and W211 into X2. Okay, I suppose this is clear. This weighted sum point is clear to everyone, right? Yes or no? This weighted sum point is clear or not? Okay. And later, the value of Z1, the value change in value of Z1 will impact the values of H1. Okay. what is H1? H1 is sigmoid of Z11. That is sigmoid is, so this is the weighted sum that we are calculating, and later H1, that is the output of the hidden layer, will be the sigmoid of this weighted sum. Similarly, output of the hidden layer 2 will be sigmoid of the Z of the weighted sum of Z22. Okay. Since H1 will be impacting, the values, the changes in the H1, will impact the value of Z2. What is Z2? Z2 is ultimately W12H1 plus W22H2. Okay, that is the value of Z2. So the change in the value of Z2 will impact the value of Pi hat, and Pi hat, change in the value of Pi hat will impact the value of loss. So this is the chain rule. This is how it will go from here to here, and then from here to here. Okay, so ultimately what will be happening is W11, change in the value of W11 will impact the value of Z11. That is this weighted sum. The weighted sum value will impact the value of sigmoid, that is the output, that is of the hidden layer. The change in the value of output will impact the weighted sum that is being calculated in the output layer, that is Z2. And the change in the value of Z2 will impact the value, that is the output, that is being calculated in the output layer, that is Pi hat, which is sigmoid of Z2. And later the loss. Okay, this chain rule is clear to everyone? Yes or no? Any doubt here? Okay, what about others? Is it clear? How this process is going, this chain rule, how it is going? Okay. Okay, so if you try to calculate the values of this particular derivation, you can easily obtain the values of the derivation. Now you have the values. So here you can see we already have the values of this one. Okay, we have this particular value del Pi upon up to this we have the value already. Up to this we have already calculated the value. So if you can see, what is this value? This value is actually the error associated with the output. Sorry. Yes or no? That is being added along with the error, new error that will be along with the gradient, along with other values. Yes or no? This is the error in the last that we had calculated previously for the output layer. Yes or no? Are you getting my point? Okay. See, so this derivation formula that we have calculated, if you recall, in this particular point, up to this value, I guess up to this, maybe up to this value is the error that we have already. This values that we have already calculated in the previous formula that we derived for the gradient in the case of output layer. If you recall, gradient in the case of output layer. Yes, which is being added in the gradient that we are calculating for the hidden layer. So ultimately, this gradient is being propagated backwards, right? Are you getting the point? Yes or no? Is this clear to everyone? Just let me know those of you who are not getting, so that if you are not getting, just don't hesitate, just ask in the classroom, so that we can solve the doubts at this point of time immediately, right? Okay, so the point here is, all right. So we have already calculated this error. We have calculated when we were performing the gradient. We were calculating the gradient value for the output layer. So ultimately, we can say that this gradient value is being propagated backwards. The gradient that we have calculated in the output layer is being propagated backwards in order to calculate the gradients that are present in the hidden layer. Okay, hidden layer means the connection between input layer and the hidden layer, right? So this we can also see in the chain rule that we have created for the case of the hidden layer. We can also see in the chain rule that we have created that the error that is being calculated in the output layer is being propagated backwards, that is in the previous hidden layer, right? Okay, so I suppose that you can calculate the values that are present with you. The gradient, the derivation values you can calculate by yourself also. And these values we already have. This del P, suppose the first this is the value that was already calculated in the case of output layer. Okay, these are the values that were already calculated in the case of output layer, and these values we have new values that we have calculated based on these two derivation, del z11 upon del 211 and del h1 upon del z11. Okay, are you getting the point? This is the derivation, this is the gradient value for the case of del li upon del w211. Are you, is it clear now? Is this point clear now? Okay. So already it is written also that we can see that we are propagating the error of the last layer into the hidden layer to calculate the hidden layer error, or we can say that we are propagating the gradients backward in order to calculate the gradient of this particular hidden layer. Okay. So similarly, we have calculated in the case of del li upon del w211. Similarly, we can calculate for other values as well, where we are going to propagate the error backwards. So in the case of del 121. This will be the value where we'll be propagating the gradients backwards. Okay, so up to this everyone is clear. This is just an example through I explained the derivation, the entire derivation through an example that I took. That is an example of a multi-layer perceptron that we created for ourselves to understand the concept of derivation. So that whenever you go through, if you go through two of the textbooks that is suggested to you, one is by Tom Mission. If you go to the derivation, you might find the values that is given to you, that is the initialization and the subscript value that is given to you, del I, j. You might find it confusing, but now it might be clear to you that how this whole process is being done, right? The whole chain rule is being done. You may go through different books as well, which is for your own references, that how this whole process is going on. So today we'll be going through that what is given to us, the backpropagation, actual backpropagation algorithm that is provided in your reference book that you are studying, and we'll solve a particular sum for this backpropagation as well. But before we proceed, are we clear that what we are doing in the case of this particular example? Then we can proceed with this particular part. So are we clear with this whole thing up to this? Okay. All right. Okay. So I suppose others are also clear with this whole thing. So, all right. So here is the backpropagation algorithm that is provided to you whenever you go through your reference book. This is the backpropagation algorithm that is given to you. So here we have used different subscripts. For example, just go through the algorithm that is given to you. Each of the training example will be in the pair of x comma t, where x is the vector of network input values and t is the vector of target output values. So whenever you have a large data set that is given to you, the large data set will be in the form of many high dimensional data. Will be, so whenever you are doing in the real time multiplication or performing the derivation, it will be in the matrix form. Okay, this is just not provided here, but it will be in the matrix form. That's why the term vector of networks will be using the vectors in order to perform the derivation and all, right? So we'll be having in the data set will be provided to you. Will be having inputs as well as outputs associated with it. Okay, inputs as well as outputs associated with it, and there will be a learning rate. And there are all the connections, all the connection in your multi-layer perceptron will be so all the neurons in your multi-layer perceptron will be connected to each other. So we already discussed that this will be a dense kind of connection where all the neurons are connected to each other. So it will be a dense kind of connection, right? And we'll be first performing the forward pass. So here the input from unit 1 to unit 2 will be denoted at xji. So all these notations are given to you, but just be clear with the notation. Okay, now you might be aware that what are these notations mentioning and what are these notations talking about. So these are some of the notations that are given to you. Just go through the notation whenever you perform, whenever you study for your exams. Just go through the notation thoroughly. Okay. So for there are in the feed forward network, this is also known as a feed forward network kind of thing. where we'll be having an input and hidden and an output. Okay, we'll be having input layer, hidden layer, and output layer associated with our multi-layer perceptron, right? So for each of its training example, what we'll be performing is input the instance to the network and compute the output of every unit U of the network. Okay, every unit U means, for example, at this point of time, we have only one unit associated with the output. We may have, for example, in the case of softmax regression, for example, in the case of softmax based calculation, you may have multiple outputs. Okay, multiple outputs may be associated with your multi-layer perceptron. At this point of time, we have only one neuron in the output layer, but we can have multiple neurons also in the output layer, right? And for each network, and after this is the forward propagation. Okay, this is the forward pass that we'll be doing. First point that we have is forward pass. That is, we are propagating the input through all the network, all the layers of the network. That is through the input layer and the hidden layer and the output layer. And then we are calculating what is the error associated with the particular model. Okay, what is the output error that is being produced? Then how far is the predicted output from the actual output, right? From the actual output. Then we propagate the error backwards towards the network. That is, we are calculating the error backwards. That is, we are calculating what is the error with the hidden layer and what is the error with the output layer. Sorry, this is for the output layer. What is the error with the output layer and what is the error with the hidden layer? And then we are calculating the weight update rules. Okay, everyone is clear with this? Yes or no? So this formula that we are given here, now you can understand that what is this formula. If you can make this comparison between what we did in the derivation and what is given in here, now you can see that what is given here, right? Yes or no? Are you able to see the derivation properly? That OK is the output that is being created. Let us just go through. OK is the output that is generated through the model. TK is the output that is target output that is given in your data set. Okay, and W is the weight associated with each of the connection. So can you now see the output, see the derivation that we had done in the case of our example? Are you able to picturize this? Yes or no? Okay, we'll go through the entire process that is given to us. But are you able to get a brief picture that we did in the case of our example and what is given to us in the case of hidden layer as well as the output layer? So here that is a weighted. Here that is a sum. Here sum of all the k the error as well as the weight is given to us. So if you see in the example, just a minute. So in the example that we had done, we had two inputs, two hidden layer and one output layer. Okay, so whenever we are trying to calculate the weight associated with this particular, update the weight associated with this particular connection, we were calculating what is the error that is being propagated by this particular node to the output node. So for example, there is only one layer of connection with the output layer. So we were adding this particular output. We were adding this particular gradient value with the gradient value that we are calculating for this particular weight. But if we have more than one connection, for example, we have 2-3 output units associated with the output layer. Suppose this is 1 and this is 1. Okay, then we have to add for all these values. That's why the sum Wij into del j is given here. Okay, in the backpropagation algorithm, there is a sum of k belongs to output. That is, k belongs to output means for each of the output neuron error will be added in this particular, will be added and will be propagated backwards. Each of the output will be added and will be propagated backwards. Are you getting the idea? Yes or no? Yes, need to follow the same process for other neurons as well. So since we are calculating the weight, updating the weight associated with this particular neuron, with this particular connection. So what we'll be doing is for this particular hidden layer, we'll be checking that this particular hidden layer is going to impact the error for how many output for this is going to impact the how many neurons. So if we have only one neurons, if we have only one neuron in the output, only one of the weight will be added in the gradient calculation for the connection between input layer and the hidden layer. But if we have multiple outputs, then we'll be adding this value, this output that is calculated for this particular output, the gradient that is calculated for this particular output will be added as well. But for example, suppose we are calculating the weight update rule for this particular value, for this particular connection. Then for this also, we'll be having connection with this, with connection with this, and connection with this. And we already discussed that in the multi-layer perceptron, all the neurons will be connected to each other. That is, you will be having a dense connection here. So here also, if you are trying to calculate the weight update rule for this particular connection, then what we are trying to back propagate, we are trying to back propagate the error that is being calculated here, error that is being calculated here, and error that is being calculated here. In short, all the connection that are associated with that particular hidden neuron. This particular hidden neuron ke saath, how many connections are there? This connection is there, this connection is there, and this connection is there. So all these particular values will be summed and will be propagated backwards. Are you getting the idea now? Okay. What about others? Are others getting the idea now? Why we have the sum process here? So in the example that we took, we had only one connection with the output. So in this case, only suppose we are calculating the weight update rule with this, then this hidden layer neuron is going to affect only this particular output neuron. So only this value is being propagated backwards. But if we had multiple neurons in the output, then all the neurons that is being affected that this particular hidden layer will be propagated backwards. Are you getting the idea? That's why this sum value is over here in the calculation for hidden layer neuron, hidden layer unit. Okay. Yes. Is it clear? Okay. So let us go through the derivation part that is given in your reference book once, so that you get the idea and you can relate that what we have done and with the what is given to you in your reference book whenever you study through this, right? So that is some of the points that are given to you is an input node. An index is assigned to each node in the network, where a node is either an input to the network or an output of some unit in the network, right? So your index, that is an integer that will be given to you. That is, for example, that is whatever connections we have, whatever for input units, we'll be having xi, I or j. You can use any integer value to assign to it. And xij denote the input from node I to node j, and wji denote the weight corresponding weight. Okay. So for example, this is the weight. For example, this is the new multi-layer perceptron that we have. So W12, for example, I said this is W12. So I'm stating that this is the connection from 1 to 2, but here they are going for WJI, where 2, I'm denoting J here, I am denoting 1 here. This is the layer 1. I am denoting 1 is I is equals to 1, J is equals to 2, which denotes the layer. Okay, which denotes the layer. So these are some of the notations that are given to you just to understand. So whenever you go through the derivation, you consider this notation clearly, right? And del n is the error associated with each of the nodes. Del n is the error associated with each of the nodes. And del n is equals to, they are saying that del n is equals to del e minus del e upon del net n. Okay, we'll see that why it is net, because of negative, because of the sign that we are getting in the calculations that they are doing. Because of that, they have a negative sign given here, right? I suppose these points are clear to you, right? Yes. Okay. So in the next part, some of the important important notations are defined to you, where xji is the input to the ith input to the unit j, weight associated with the input ith input to the unit j, and net j is similar to what we talked about z2. Okay, net j is actually weighted sum. Okay, what we talked in the z value which we were talking, that is similar to net value, right? Oj is the output that is generated by unit j. Oj is the output that is generated by the unit j, that is whatever output that is being generated by a particular unit. For example, in the hidden unit, what is the output that is being generated? For example, in the hidden unit, z is the output that is being generated, or h1 is the output that is being generated in the particular hidden unit. In the output unit, the output will be the output that is being predicted by the multi-layer perceptron model. Similarly, Tj is the target value for the unit output unit, for the output unit. Okay, and sigma is the sigmoid function, and outputs are the output associated with each of the final layer of the network. And downstream, that is a function that they are talking about downstream, which is the set of units which whose immediate inputs include the output of unit j. So for example, in the case of hidden layer that we discussed here, this is downstream. What are the downstream that are associated with this particular hidden unit? That is first connection 1, connection 2, and connection 3. These are the downstream that are associated with the unit I, this particular hidden unit I, that they are talking, that they are mentioning as downstream. Are you getting the point? Yes or no? Okay. So this is a loss function. They have defined a loss function where loss function is the actual target value minus the predicted target value, the whole square, and the gradient value. Okay, del wji is the gradient value, and it is minus of the learning rate into the gradient value that we are going to calculate. That is the await update value that we are going to calculate. So if you recall, in the case of linear regression also, what was the weight update rule? Weight update rule was delta theta j is equals to theta j minus alpha into del del j upon del theta j. Okay, so this whole thing is actually your weight update, which they are mentioning here. Are you getting the idea, right? Yes or no? This is clear? These all notations are clear to everyone? Okay. So first thing that we'll be doing is, for example, that whenever we are calculating del ed upon del w ji is equals to, this is the value that you are getting. That is del ed upon del net j and del net j upon del w ji. Yes or no? Are you getting the point? So weight update, the weight value will be impacting your z value, which they are talking about the net value, which they are mentioning through net value, and the net value will be affecting your, this z value will be affecting your what? Will be affecting your output value, that is pi hat. Okay, which will come to later. But this derivation, this the formula that is given to you, is that clear to you? This chain rule is clear to you or not? Tell me if it is not clear. Anyone who is not clear with this chain rule? See, I can understand. Yes. Okay. What is ED? ED is actually this loss. Okay. ED. Okay. Wait a minute. Okay. If you see, ED is the loss. ED is the loss that is loss that is defined. So in our case, the L was the loss that is defined. Here only different notation is being used, which is ED. Okay. Are you getting this? Okay, so I can understand if it is getting a little bit clumsy to you in the case, since if this might be getting a little confusing for many of you. But what I would suggest is you go through the derivation. I'll share the PPT by today itself. I'll share the PPT. So in the next lecture, if you have any difficulty, you may ask in the next lecture as well, and go through it once so that we can further discuss properly. If many of you might be finding difficult to understand the derivation and all, so it is actually very confusing for many of you. So I'd suggest that I'll share the PPT and you go through it once and let me know whether the sequence what I was talking about in the classroom is understood by you or not. So be sure that you be present in the next lecture and that convey that what you are understood, whether you have understood or not, right? So up to this, everyone is clear. This chain rule is clear to everyone or not? This particular chain rule that is given to you. Maybe the PPT is. Okay. Okay. Is everyone clear with this chain rule that is given to us? That is a loss, the gradient, that particular weight update rule for this WJI, whatever the weight update rule. Okay, this particular weight update rule we are calculating for the output layer. Okay, for the output layer means for the weight update for the neuron, that is the connection that is present, the weight connection that is present from the hidden layer to the output layer. For that particular, we are calculating the gradient value. So WJI may be any value. Okay, for example, this connection could be there, or this particular at this point of time, if we have only one connection, one output neuron associated with it, then these two weight update values could be there. Okay, these two weight values could be there in the WJI. Okay, are you getting my point? What I'm trying to convey, right? So WJI, the loss value with respect to whenever we are trying to perform the chain rule. So if you recall, we already did in the case of our example that we did, which was the loss, the update in the value of weight will be impacting our Z value. That is our weighted sum value. And our weighted sum value will be impacting our output value, that is PI hat that we were calculating. And here that PI hat is the OK. That is, it is being denoted by O subscript K, and that OK value will ultimately impact our loss value. Okay, are you getting the point? So this is the derivation that is given to you. If you see, I guess. Okay, this is the derivation that is given to you. So if you see, we already saw. So the del Z2, this net value, the derivation of net value with respect to the weight value will be equals to our input value, right? So in the case of that one also, we also already saw Z is actually what? The weighted sum of weights and the input value. So if we are performing the derivation with respect to weight, our output will be the input value, right? Yes or no? This particular derivation is clear to everyone, right? I suppose. How this is xji. Okay. Okay, so further after this, we can perform the derivation for the first part, that is loss with respect to the net j value, that is the weighted sum value, which is ultimately another chain rule, which is we already discussed. We already discussed that del loss with respect to the output and output with respect to the z value, that is net j. And we already know what is the derivation of loss with respect to the output value, which is minus tj minus oj. Okay, this derivation is already clear to you. We already did that in the case of the example that we did, right? And for the respect for oj, that is output, oj with respect to net j, we know that this is a what is oj? Oj is actually sigmoid of net j. If you perform the relation with the already discussed example, you will be able to understand it clear. Now is it clear, right? So which is actually sigmoid of net j into 1 minus sigmoid of net j. Okay, which is being mentioned here, oj into 1 minus oj, and the whole value is actually del ed upon del net j is equals to minus tj minus oj into oj up into 1 minus oj. Okay, up to this, is everyone clear with this derivation that we have come to? Yes? Okay. Okay, so ultimately your gradient value that we had to calculate, which was del wji, is equals to the eta of the minus into eta del ed upon del wji, which is actually this value. Okay, this is the value that you are getting. Just this is the value that you are getting. This is for output layer. This is for output layer. And if you recall, this is the loss, this is the del j value that you had calculated in the case of back propagation algorithm that is given to you in the initially we discussed the back propagation algorithm that is given to you. Del k for the output layer is equals to ok into 1 minus ok into tk minus ok. Okay, this is the loss associated, this is the error associated with the output layer, which we have here, which we have derived here. Yes or no? Are you getting? Are you able to relate now? Okay. Yes. Now, in the case of hidden neuron, this is the derivation. Okay, yes, Priyank, it is getting confused. So, till when are you clear? Up to what point were you clear? From where this is getting clumsy? Yes. Okay, example that we had discussed was clear. So see, try to relate that particular example with this particular. See, what is the difference that we are? Why did I go through the example first? Is because directly going through the notation would be some of the term that is this is known. Okay, and yes, see, directly going to the notation that is given to us would be quite confusing. That's why I went through the example so that you get the idea. That is how the chain rule is being worked, how the chain rule is being implemented, so that now we can matching with the example that is not much clear, right? Okay, Priyank, fine. I'm getting the point that is you are trying to make, but see what we are trying to do here is here also we are trying to perform here I'm just trying to perform the relation that we have already discussed in the case of an example that we discussed. This is a generalized form. Okay, whenever you are given a large set of the one we discussed, the multi-layer perceptron that we discussed had one input layer, one hidden layer, and one output layer. But we have to calculate a generalized. This is a generalized form of output. This is a generalized form of derivation that will be performing. So this is similar to that we discussed in the previous also. So here also, if you see, this is the loss function. This is first we have to calculate the gradient with respect to the weight associated with the hidden with the connection from hidden layer to the output layer. Okay, we have to calculate the gradient associated with the weight associated from the hidden layer to the output layer. So here the chain rule will be similar. So what they are trying to do is the chain rule will be so if you are trying to make any changes in the weight associated with that, it will ultimately make the changes in the weighted sum, that is net j. They are talking about net j, and this net j will ultimately make changes in the pi hat. So here they are mentioning pi hat as oj. Okay, so ultimately that is the chain rule that we have derived, and the same chain rule we are trying to implement here. So we already know the loss function that is present with us. And if we perform the derivation with respect to loss function, this is the value that we are getting with the derivation with respect to loss function. And we also know what is the derivation of output, OJ. That is OJ. If you relate the OJ with PI hat, then OJ is actually, PI hat is 1 upon 1 plus e raised to minus Z2. And OJ will be actually 1 upon 1 plus e raised to minus net J. That is weighted sum. Both are actually same. Net J and Z2 are actually same. So here also the derivation value will be similar. There we had pi hat into 1 minus pi hat. So here we have oj into 1 minus oj. Are you getting the point? We are trying to this is a generalized form of derivation that we are getting. That was for a perceptron that we had defined in the previously. For example, that we are trying to understand through the chain. Okay, now is it getting clear then? The point is getting clear or not? Yes, okay. So similarly, so we have calculated. So now we have calculated the weight update rule for the case of output layer. We have calculated the weight update for the case of output layer. So we have calculated del Wji for the case of output layer. So we know that how to update the weight. W new will be equals to W old plus del Wji. Okay. So this we have calculated. So we can calculate the what is the weight update rule for this particular weight. We can calculate now. Okay. Are you getting the point? Now, similarly, now we have to calculate for the hidden layer. Now we have to calculate for the hidden layer. Okay. So in that case, if you recall, in the case of hidden layer, we had discussed that we are going to propagate the error backwards. So here also what is being done is we are going to propagate the error backwards. That is, it is performing the summation. It is performing the summation for all the errors that are present from the hidden layer to the output layer. That is being passed from hidden to the output. So for example, in the case of example that we had discussed, only one of the connection. For example, if you are trying to calculate the weight update rule for this particular connection, then only one downstream value will be added in the particular error. But suppose if we have more than one neurons in the output layer, then all these values will be added to the hidden layer to this hidden layer, particular hidden layer. So that is what it is given to us as k belongs to downstream j. Downstream j means what? To all the values that are present, all the neurons hidden, all the output neurons that are present. So for example, if you have only one output neuron, then only one gradient value will be propagated backwards. But if you have multiple output neurons and all the connections, so all the gradients that are being calculated from the hidden to the output will be propagated backwards. Are you getting the point? This particular, are you getting this? Yes or no? Yes, everyone, just let me know. Yes or no? Okay, fine. So we'll keep this particular point for the next lecture's discussion. Up to this, we have discussed. I suppose that everyone is clear with this particular point. We'll keep this derivation for the next lecture, and we'll share this. We'll also solve a particular sum that we are going to which we are going to understand the whole calculation. And I'll share the PPT today itself. So I'll share. Yes, I'll share the PPT today itself, so that you will get, so go through the derivation, go through the entire derivation, and we'll solve a particular sum in the next lecture, so that before the next lecture also, just let me know if you are facing any difficulty in the derivation or understanding any of the particular concept. But before that, I suppose that everyone is clear that what is this particular whole back propagation theory is about. I suppose everyone is clear with the theoretical concept and with the hidden layer, what is output layer trying to do, and what is the input layer trying to do. Okay, everyone is clear with the theoretical concept at least. Okay, nobody is having any doubt in that particular part, right? So the derivation part I will be uploading today, so that you'll get a better picture. And by the next lecture, please come up with any of the doubts that you have, so that we can clear it at that point of time. And also with the evaluation instruction, I'll give it again, that please upload all the GitHub repository links in the evaluation one, and add me as a collaborator in your GitHub repository, so that I can see your work. But you have to upload your links. Okay, only that the links now will be now your repository will be private. Yes. Yeah, see, the backpropagation is not linked with linear regression. I'm just, what I'm trying to do is, in the case of backpropagation, where we are utilizing the gradient descent algorithm to calculate the gradients, I'm trying to relate that particular point with the linear regression. Okay, I'm just trying to relate. In the case of, I'm just giving an example of a linear regression in order to make you understand that how in the linear regression part, we were calculating the error values, and then we were calculating the gradient values to update those gradient values by updating the values of those weights associated with the parameter values. We were trying to find out the optimal parameter values to minimize the loss. In this case also, we are trying to do the same process, but in the back propagation, what we are trying to do, which is different, we are ultimately trying to find the optimal values of parameters to minimize the loss. But in back propagation, what we are doing is, there is specially for the hidden layer. Okay, especially we are doing for the hidden layer, because we do not have any error associated with the hidden layer. That's why we'll be propagating the errors that we have calculated in the output layer backwards, so that we can get errors associated with the hidden layer. Are you getting the idea now? This is just in relation that I'm creating with the linear regression for the gradient descent part. Okay, so right now I'll be ending the meeting, and I'll share the PPT today itself, and just keep checking the Google Classroom, that is your classroom, for the update regarding the evaluation. Otherwise, just be clear that in this week's lab, you might be having your evaluation. That is your first evaluation you'll be having. So just be ready with your preparation for the evaluation, right? Okay. Otherwise, I'll be sharing whatever update is there, I'll be sharing in the classroom. Okay. Fine, I'll end the meeting now.